Hey guys, I'm going to walk you through the problem here today for the Rocket Launch Lab. This is going to be for the Rocket Launch Lab. And in the Rocket Launch Lab, you're going to launch a projectile that is going to leave the ground, it's going to go up for a while, and then it's going to come down. And you are going to know how far the thing went, and you're going to know how long it stayed in the air. That's pretty much the only data you can collect with this because we're going to be throwing something. So we're going to know how far it went downfield and how long it stayed in the air. And from that, we're going to figure out its total speed at launch. I'll review what that means in just a moment. We're going to figure out its horizontal speed at launch, its vertical speed at launch, and figure out how high it went. So using our knowledge of projectile motion, we are going to use this information to figure out all of this. And we're going to be doing it with an actual projectile that you throw. So you're going to have some real data. But this is just some numbers that are fairly round so that the math is a little easier to see. So I'm going to walk you through this. Now, it turns out, let's see, first off, let's show this thing. This is the worksheet you worked on last time. This is a projectile. In this particular example, it was a person throwing a baseball. It goes up for a while, it comes down for a while. And again, we're saying it goes 90 meters downrange. Guy's got a good arm. And it's in the air for 6 seconds. And this is given on this worksheet because he throws it, it goes up 1, 2, 3, comes back down 4, 5, 6 seconds for the whole trip. So this is where we're coming from. So the first thing we're going to do is figure out the horizontal speed. You might want to be taking notes on this, by the way, and pausing the video from time to time so that you don't have to rewatch this when the time comes. So go ahead and pause it when you catch up. So this is for horizontal speed. This is the easiest one. We are going to use speed is equal to distance divided by time. Now remember, when you're talking projectile motion, I still have this thing, horizontal motion is independent of vertical motion. So however fast a thing is moving horizontally, that never changes. The vertical motion does change because gravity is changing as it goes along, but the horizontal motion is always the same. So in this problem, the projectile went 90 meters in 6 seconds. So this is 90 meters in 6 seconds, and that comes out to be 15, I believe. 90 divided by 6 equals 15 meters per second. Okay, so that is the horizontal component of its speed is 15 meters per second when we launched it. Okay, now to get the total speed, we have to know the horizontal component and the vertical component. So we're going to have to do this one next. So for the vertical speed, this takes some physics. We actually have to think about what's going on in the real world to be able to know what math to do. So here's, well, actually I can use this diagram right here. It's in the air for 6 seconds. So it is, well, it's easier to see in this. When we throw the ball, it goes up for 1, 2, 3 seconds, and then it falls down for 1, 2, 3 seconds. So it spends half of the time going up and half of the time going down. Now, if we kind of freeze frame it at the apex, at the top of its trajectory, this is just like we dropped the ball from the top of the trajectory. And then it fell for 3 seconds. It started here and then falls straight down for 3 seconds. And the question now is, how fast is it going when it hits the ground? This is a good way to think about it because the speed that is going up is the same as the speed that is coming down. But it's easier to think about if you think about only the part where it's falling down. And if you can figure out how fast it's going when it hits the ground, well, that has to also be how fast it's going when it goes up. Now, there are other ways to solve this, but that's probably the simplest one conceptually. So it falls for 3 seconds, and the acceleration is equal to g because it's in free fall. We're allowed to use 10 for this one. So the equation we're going to use is speed is equal to acceleration times time. And the special case in this one is v equals gt. So the final speed is equal to 10 times 3 seconds. This is meters per second squared equals 30 meters per second equals the vertical speed. Okay? 30 meters per second. And this shouldn't be too surprising because in this example problem that you were working with before, it was given that the initial speed was 30 meters per second. So when we work the problem backwards, it's a little reassuring that we get the same vertical speed for the line. So to sum this up, to get the vertical speed, you take half of the time airborne. It was airborne for 6 seconds. You take half that time because it's spending half the time going up and half the time coming down. And the half of the time that is spent coming down, you use that to figure out how fast it's going when it hits the ground. That's the vertical speed. Now for total speed, now we're adding vectors. When we launched it, it was going up at 30 and sideways at 5. And we use Pythagorean theorem, a squared plus b squared equals c squared. This is the total speed. And for this one, we get 30x squared plus 5x squared equals, we take the square root of that, and it comes out to be 30.4 meters per second. That's the total speed. All we did was Pythagorize the two components we figured out here. The vertical component plus the horizontal component. We got to use Pythagorean theorem and you get 30.4 meters per second. Now, finally, we have the how high question. How high did it go? This distance here. For this one, we use the same mental trick that we did for the vertical speed. We recognize that it spent half the time going up and half the time coming down. So it was falling for 3 seconds. Falling for 3 seconds. G again is 10 meters per second squared. And now we have to know a distance that the thing fell in a given time. So the equation we use for that is d equals 1/2 gt squared. The distance is equal to 1/2 times 10 times our 3 seconds squared, which is 5 times 9 equals 45 meters. You can run that through your calculator if you don't believe me. But this probably seems familiar when you're doing your free fall exercises before. And an object which is in free fall for 3 seconds falls for 45 meters. Now, obviously, the numbers that you're going to have when you do this lab are not going to be so neat and round. So the numbers you're going to get may not be so neat and round. That's okay. That's just what math does. But yeah, so this is the process that we go through for crunching the numbers in the rocket launch lab. What I want you to do for practice now is to do this. Imagine you're throwing a football and the ball flies 55 meters in 3.1 seconds. And you want to figure out the vertical speed at launch, the horizontal speed at launch, and really the whole thing because we're ignoring air resistance. Figure out how high it went and the total speed at launch. You're going to use the same method for this that I just showed you for this. So the numbers are 55 meters in 3.1 seconds. I want you to figure that out, crunch those numbers, show me the work, something like this, make an image of it and send it to me. That's your homework for tonight. All right.